Greetings everyone! Today I'll be showing you PhraseFormer, a web service for paraphrasing using deep learning. First, we show the motivation for the project, a high-level description of the tool, and some examples that may surprise you. Then we see the network architecture used to build the front-end and back-end of the project. Then follows a description of the model and algorithms in use. Finally, we share our conclusions and further work. Now, have you ever been in a situation where you say the following to yourself? How did I say this in a different way? I need to use a different word here. That way doesn't sound too well. This title sounds boring. There must be a better one. Well, these kinds of situations can be very difficult to address in a straightforward way. And so, we need a tool that aids you in your writing by providing variations of your original sentences, phrases, or ideas. Meet PhraseFormer, a paraphrasing tool for creative writing. It uses a contemporary deep learning model and a special decoding algorithm to generate variations of phrases and text into sentences that hold similar meaning or context. Before showing the tool and how it works, I'll give you a little test to see how well can you spot the model at work. This is a thumbnail of a YouTube video made by Thought2, a well-known content creator. Here we see many titles. One of them is the original one. The rest are variations produced by the model. Can you spot the real one? Pause the video if you like. Now, I will show you the original title and its variations produced by the model. This is a snapshot of the website that serves as the front end for the service. As you can see, it shows the original phrase and the variations below it. The website offers the option of trying a random quote to test how it works. Optionally, we may also adjust some settings like variation level and words that we may want to exclude from our results. Honestly, this was not the most fair test, but how did you do anyway? As you can see, the tool is able to create fluent variations of the original text. It can change the order of the words, find synonyms, and even extend the sequence with relevant words. Let's try another input sentence and see if you can spot the model now. This is another video from the same creator. Can you spot the real title? Again, you may pause to think about your answer. Got it? Actually, it's the first sentence, but wasn't it hard? But then, how does this work? Don't worry, I'll show you how this service works. Let's see how the network part is built. The users access the website made using the React.js framework with the Material UI library to make a friendly and responsive website that exposes the service. Internally, this website uses a web client called Axios that sends requests to the server that holds the model. These requests have one required sentence field that holds the text to be used for paraphrasing and two optional settings that will be discussed later. The benefits of using a REST server instead of just accessing the service through the website is that any programmer capable of making HTTP requests is able to access the service. The server runs on an Anaconda environment for Python. We use the Flask Python library to process requests. These come in JSON format and are transformed into Python variables. Then we send the text and settings to the deep learning model. This model uses two Python libraries, PyTorch, which is a deep learning library, and Hugging Face transformers, which can import, use, and fine-tune pre-trained transformer models. We'll discuss these models shortly. Let's talk more about the deep learning model that is used to produce these sentences. We introduce BART, a model made by the Facebook research team. It stands for bidirectional and autoregressive transformers. It is based on the transformer model shown in the left picture. The bidirectional encoder takes a sequence as an input and finds the relationship between all the words in the sequence. The relationships are then encoded into a context representation that will be used in the decoding process. The autoregressive decoder uses this context to create sentences by finding the probability of every word appearing next in the sequence based on the previous words. Then we choose the words with the highest probability and repeat until we get the end of sequence token. So for example, if we input the sentence, "Today is a sunny day," into the encoder, and then we put the sentence, "Today is very ... the word sunny will have a lot of probability, and the word chocolate will probably have low probability. We take the most probable word in each step to generate a sentence. This model was trained by taking a text, then mixing and masking it, and then reconstructing it. This makes the model pretty good at things such as summarization, translation, and comprehension. This model has a tendency to simply recreate the original sequence, so we repurpose it to a different decoding algorithm called group beam search. Instead of creating just one sequence and choosing the word with the highest probability each time, we start many sequences with a special start of sequence token and gradually build them. These sequences are arranged in groups. Each sequence is passed through the decoder to generate a set of probabilities. There is a probability for all the words in the vocabulary, so this vector has more than 50,000 values. To generate different sequences, we pass the probabilities through a filter that changes some probabilities and even makes some of them zero. These filters work differently for every sequence. After we get the filter probabilities, we take the word with the highest probability to make the new sequence of the group. If a sequence has the special end of sequence token with the highest probability, then we finish that sequence. The process ends when all sequences are finished. These are some of the filters that are applied to the probabilities. These are responsible for making the results more varied and interesting. Let's see how they work. This is the dynamic blocking filter. It works by creating pairs of words based on the original sequence. For example, the start token goes with the with chart with above, and so on. Then, we randomly choose some of these pairs, typically 50%. As we follow the decoding process, we make sure that these pairs of words do not occur. So, for example, if we see the word has, we reduce the probability of the word changed to 0. In our case, we have a different set of pairs of words for each group of sequences. This filter works especially well with this model since it assigns a very high probability to the original sequence, but if we block the prediction, we find interesting ways in which the model attempts to solve the sequence. Here we have some results using the previous example. Some of the settings that the user may adjust to make more custom results are the diversity and the excluded words. Each of these parameters belong to a specific filter. The banned words filter works in a similar way as dynamic blocking, but in this case, we have specific static words. This filter is also the same for all sequences. Finally, the diversity is a number from 0 to 1. The diversity filter is aware of all groups and all sequences. It uses this parameter to gradually reduce the probability of words appearing in earlier sequences or groups, thus creating more varied sequences and increasing the diversity of the results. Here are some results from the previous example, but blocking the words illustrates and world, and setting a diversity of 0.1. If we further develop and refine the methods using this project, we may use them in the following fields. We can make more varied natural language generating models for chatbots to make responses more varied, but keep the same ideas. Text simplification can be thought of a subset of paraphrasing, and so we may, for example, block unnecessarily complicated words and reproduce complicated sentences in simple terms. We may also use this method to extend question answering datasets, much like how input is sometimes distorted in image processing. We can find variations of questions that result in the same answer to increase generalization. Finally, this was a great project, and even though I did a lot, I learned much more than I did. I hope you liked it.